this session. So I'm turning that on right now. Okay, so those prompts obviously are certainly accessible, and we encourage you to engage with those, moving forward. But now I'm going to move into the actual material today. So the topics that we will cover, I'm going to take a bit of a brief look at all 5 of these. So tools and libraries for compiled language GPU codes, meaning Fortran, C, C++. We'll get into sort of interpreted language GPU programming in Python towards the end of this workshop series. We'll talk a little bit about accessing GPU software on Casper. So this is Casper specific since it's an NCAR workshop, but I think a lot of the techniques that you might use to access the software will be similar on other systems. Compiling GPU code with the NVIDIA HPC compilers, simple compile and runtime diagnostics that you can perform, and then just a brief look into writing makefiles to build GPU codes. So you've had a lot of context in the first 3 sessions, so I'm not going to belabor it too much, but just to give a bit more context, the GPGPU software development ecosystem is certainly growing and it's diversifying. So if you go back to 2007, that's when NVIDIA released its CUDA toolkit, and this was really the Kickstarter for the growth in the software and GPU software development. The CUDA toolkit has seen many releases since then and many add-ons, and it's really grown into quite the ecosystem. But they were really the only player in town in terms of that until 2016, when AMD released their sort of equivalent ROCm set of tools and libraries. And that has seen a lot of development in the past couple of years as they've ramped up their GPGPU efforts. And in 2020, NVIDIA released a larger set of software called the NVIDIA HPC SDK, which includes the CUDA toolkit, as well as compilers and some profilers and debuggers. And Intel is also getting in on this as well with their variant of the One API set of tools. And that's going to be part of their plans to support their GPU, their GPGPU hardware that's coming out. So you probably get the idea here that SDKs are typically designed around specific GPU architectures. And since we run NVIDIA GPUs currently at NCAR, NVIDIA's HPC SDK is the primary set of tools for building and analyzing GPGPU code at NCAR. So if you recall from last session, Brent showed this diagram, or a very similar diagram, that was an overview of all of the components of the NVIDIA HPC SDK. So what does it include? It includes a set of compilers, as well as core libraries, including, you see like the C++ library, the CUDA C++ library. There's math libraries, including BLAS and LAPACK, and tensor libraries for the tensor cores. And then there's communication libraries as well that include traditional tools like MPI and things that NVIDIA has spun up, like the Nickel library for distributed computing on GPUs. There's also these analysis tools, including a CUDA-centric debugger and a GPU code profiler, or a set of profilers really, called the Nsight Systems and Nsight Compute. And we're going to go into aspects of these in greater detail in future sessions. The thing that we're really going to focus on in this session is the suite of compilers here. So using the NVIDIA HPC SDK, it's on a rapid release cycle, at least at present. So NVIDIA its intention is to release 7 or 8 versions of the SDK per year. So you'll see that they tend to be released every 1 to 2 months. And especially for things that are rapidly evolving, like OpenMP GPU offload and language standard parallelism, they'll make a lot of changes in each release, and they'll have bug fixes in each release. So more so than with some other compiler sets and SDKs, it's fairly important to stay up to date with what they're releasing. Now, we're doing this on Casper. If you do a module avail on the NVHPC module, which is our environment module of the HPC SDK, you'll see all these versions that are available on Casper up through the most recent February release. Now, if you load an environment module on Casper, that will add the compilers and the Nsight utilities to your path, so you'll have access to those executables in your compute environment. So NVIDIA also provides the HPC SDK in containers with the SDK installed as part of the container image. So this is pretty handy if you want to just kind of get spun up on a local system with the HPC SDK. You can just run the container using, say, Docker, or if you're on a HPC system, you can use Singularity or Podman or something like that. We're not going to go over using the container workflow there, but it's certainly nice if you want to do something that's portable, or if you want to build upon one of the images that they've provided. And those are also available at this website. So a bit about the compilers included in the HPC SDK. There are three main compilers. There's the C, C++, and the Fortran compiler. Notably, these are inherited from the former release of the PGI compilers. So NVC, the C compiler, was formerly PGCC. NVC++ was PGC++, and NV Fortran was PGF90 or PG Fortran. There is a fourth executable that you'll find in your path, which is NVCC. This is actually the C++ CUDA driver. And this is something that's also included in the CUDA toolkit. So you can still just download the CUDA toolkit and not the whole HPC SDK, and you'll have access to this command. This is, it's sort of like a processor of CUDA C++ code. And what it will do is it will call the underlying C++ compiler. So if you have the HPC SDK loaded, this command will actually also use NVC++. But this shouldn't be confused with a compiler itself, like a C compiler. This can also be used with other C++ compilers as well. So it's just something to be mindful of. Now, in contrast to C++ CUDA code, OpenACC, OpenMP, and CUDA Fortran code are all handled directly by the three compilers shown above. The HPC SDK installation also comes with a whole plethora of example codes. So here I'm just using this $NVHPC environment variable to reference the install path of the HPC SDK on Casper. But within there, you'll see an architecture directory, and then the version number 22.2. And then finally, you'll see this examples subdirectory here. And that contains a whole additional set of subdirectories with different types of examples. So I've put ones in bold here that are particularly relevant to GPU computing. So they have CUDA Fortran examples, CUDA library usage examples, standard parallelization, which obviously that you can run CPU, GPU, and then a whole bunch of OpenACC examples. There is an OpenMP directory in there as well. Unfortunately, that's currently only CPU OpenMP examples, but you could use those codes as a basis to do sort of coding practice and make them offload onto the GPU. So most of these examples include a makefile for generating binaries. So these makefiles tend to be a bit more complex than the one we'll show later, but hopefully the one we'll show later will give you enough to understand those well. I also want to point out that some of the examples in here, especially the OpenACC samples, depend on sort of helper libraries that they've included in the set of samples, and they'll get linked in at compile time. So it's best to copy the entire examples directory to your work or your Scratch or wherever you're building and running these codes, rather than trying to pick things out, unless you're very careful, you might have missing library references and you'll get weird errors. So in my experience, just copy this whole examples directory when you're ready to run through them on your own learning. So I mentioned earlier that the CUDA toolkit can still be downloaded separately. And as a result, we also still have CUDA modules on Casper. The reason that we still offer these is because they have greater flexibility and they allow for the use of it with other compilers. But it's important to note that you don't need to load a CUDA module to use CUDA when you're running the NVHPC SDK, because there is a default version of CUDA that comes with the SDK. But what those modules do allow is they allow you to customize the CUDA version when you're using the SDK. And I show an example of that here. So here on the command line, I've loaded the NVHPC module, And if I run that CUDA compiler driver command with a version, you can see that by default, I'm getting release 11.6 of CUDA. But if I then load the CUDA 11.40 module on top of this one, and I run that same command, then I'm using the 11.4 release of the CUDA toolkit. And the compilers are aware of this as well. So if I use some flags here and I say md4trans, show me my configuration, and I search for this user set CUDA variable, there's a few other ones that are indicative as well. We can see that it's picking up on that older version of CUDA that I've brought into my environment. So this allows you some flexibility in exactly which version of CUDA you're using relative to the NVIDIA HPC compilers. And again, it also allows you to compile C++ CUDA code with other compilers using that NVCC compiler driver. It's important to note, though, that the CUDA module and the CUDA toolkit only provides the CUDA toolkit and the CUDA C++ libraries themselves. So there are no compilers included, and the Insight tools are not included in that either. So for those, you do want to load the NVIDIA HPC module or use the NVIDIA HPC SDK. Now, I showed a lot of examples before. You might have noticed that there was a CUDA Fortran example, but there was not visible a C++ CUDA example. These used to come with the CUDA toolkit itself, but recently NVIDIA has split that off and distributes it in a separate Git repo. This is very accessible, but they just don't include it with the toolkit anymore. So this really provides a ton of examples. So if you do want to do a deep dive in CUDA, I would highly recommend that you check this out. You can see that there's a big section of concepts and techniques. It goes through features, it goes through libraries, and there's some performance examples as well. So there's really a lot of good stuff in here, and you can access that pretty easily if you do just a git clone on this repository. If you you can specify the branch so that it matches the version of the CUDA toolkit you're using at runtime. And this depth one, just make sure that you only download this branch instead of the files from the whole repository. But if you leave those off, you'll get all the versions when you do the clone. And then you can move back and forth within them. So we've talked a lot about the NVIDIA HPC ecosystem. I do want to do a quick mention as well that we will have a second GPU programming ecosystem on our upcoming system, Derecho. So Derecho will be much larger in terms of GPU capability. It's going to have 82 GPU compute nodes. Each of those nodes will have 4 NVIDIA A100 GPUs, and this is the next generation on from the V100 GPUs that are on Casper, and quite a bit more capable. So this is going to have quite a bit of compute power relative to Casper in terms of GPU computing. Now, it is a HPE machine with sort of Cray DNA, so it will have the Cray programming environment as one of the software ecosystems that's provided on the machine. And there's a similar diagram to what I showed earlier for the Cray software stack here. I'm not going to go through everything, but just to note that it has GPU support for both NVIDIA and AMD GPUs. Obviously, the NVIDIA part is the part that's relevant for us. They are doing a lot of active development on this, and the compiling environment in particular is projected to support these various things around these dates. So A100 support in these libraries will come in June. Partial OpenMP 5.1 support will also come in June. OpenACC 3.1 standard support should come in towards the end of 2022, with full 3.0 support coming as well in June. And it's important to note that the CUDA support is for Fortran only in their tools. So, presumably you can use NVCC with the Cray C++ compiler underneath. But in terms of native CUDA support, that's only in the Fortran compiler. And as far as what we support, so we're going to fully support the NVIDIA HPC SDK and the Cray programming environment on Derecho. So you should have 2 sets of GPU software development environments that you can use as you're developing your application. Okay, so just a little bit about requesting GPUs on Casper, and I suspect for some folks here this will be purely review, but if you haven't done so before, just a quick mention that Casper currently has two types of GPUs. There is the NVIDIA V100 Volta. This is the GPGPU, the more capable, the workhorse GPU that we have there. And in fact, there are two configurations. There's 4 nodes on Casper that have 4 of these cards in a node. And then there are 6 nodes that have 8 GPUs in each node. So that can kind of give you a sense of the resources that we have available. These are typically in high demand, especially during the workday. So we would ask that you be mindful when you're scheduling those resources. You know, if you have a job that you might just sit around for long periods of time and not use the GPU, you know, we'd ask you to think about that workflow and try to optimize it there, just to be nice to your fellow users. There are also these Quadro GP100 GPUs. These are mostly intended for visualization and analysis, although they are capable of running compute code. In fact, we'll use those later in this workshop since we're not doing any intensive GPU analysis. But don't worry, you'll use the Volta V100s in future sessions. So if you want to schedule these in PBS job scripts, this is how you would do it. You can request them using batch directives. So these go at the top of your job script, and basically you would just ask for, like, if you wanted a single GPU, for example, you would do n GPUs equals 1 in your select statement. This 1 here indicates that I want 1 chunk of these. So this is like 1 node with 1 GPU. And then I'm going to ask for a V100 in this example. And if I wanted an interactive command line session, this would be the equivalent of those directives. So I could run exec Casper, ask for a single GPU, make sure it's a V100, and I'm asking for 40 gigabytes of memory here. Now, one thing to keep in mind about these memory requests is that is the node memory. So that's the RAM that's sort of connected to the motherboard, and you can think of it as host memory. I'm asking for 40 gigabytes here to make sure that I have enough node memory to drive data to the GPU memory, which for the V100s is 32 gigabytes. So it's a bit higher, just to offer a little bit of buffer there. Now, similarly, if you want to request Casper GPUs in JupyterHub, and we'll show an example of this later, so I'm not going to belabor it too much here, but you would do a Casper PBS batch type of Jupyter server. And then it's the same type of fields here, but instead it's in a web interface. So I can ask for 40 gigabytes of memory in this field. I can ask for 1 GPU in this field, and I can make sure it's a V100 in this drop-down box here. And then I would just click launch server, and once that's ready to go, I would have access to those resources in a JupyterHub context. So with that said, I'm going to proceed with the interactive part, and we're going to start a Jupyter server in the JupyterHub and run a notebook with some example commands. So I'm going to run through this for you. So I guess I won't belabor it too much in this slide, but the steps that, if you want to follow along, you would follow these steps. So basically in a browser, you can sign into this link. You'll have to do a 2-factor authentication with Duo or a YubiKey if you still have one, as you would to sign in any of our systems. Then we'll create a named server. You can name it whatever you like, but I would probably name mine GPU Workshop, and then click add new server, and it will start it. Then for the server type, it'll be a Casper PBS batch server. And then there'll be a few settings we'll have you modify. So you can use the account code that we're providing to you as a GPU Workshop participant. For the queue, you would change that from Casper to GPU Workshop, though if you're doing this later and you're watching a recording, then you can just use the Casper queue. And then NGPUs, we'll just set that to 1, GPU type GP100, and for a wall time, 45 minutes should be sufficient here. And then when we get to the Jupyter Lab interface, we will make sure that we have the files via the Git repo. So I'm going to go ahead and do this now. And if you just want to follow along, of course, that's fine too. So now I'm in my JupyterHub servers page, and I already authenticated earlier, so I didn't have to do that 2-factor authentication step here because it was cached. But I'm going to name my my server, and I'm going to click add new server. And you'll see now I've got a selection of different types of clusters. So I will switch from a login node to a Casper PBS batch session. I'm going to change this to GPU Workshop. I'm going to use the project code for for the workshop. And in here, I'm going to ask for a single GPU. I'm going to ask for a GP100 for this. And then I'm going to ask for 45 minutes of wall time. Now, there is a 1 hour, 30-minute wall clock limit for this particular queue. So if you leave it at the default 2 minutes, you may get an error there. And then I'll click Launch Server, and hopefully after a little bit of time, my server will spin up and I will have a Jupyter Lab interface. All right, there we go. So hopefully it looks like a lot of you were able to follow the instructions to clone the repository. If you haven't, so you should land in your home directory here, unless you've done some existing JupyterHub work. There is a button here on the left, this Git button. So if you haven't already cloned the repository, you can click this, and in fact, you can put the reference, the link I gave in the chat to the GitHub repo, and click clone, and it will clone it in your home directory. If you've already done so, and you just need to pull the latest files, you can navigate into the repository here in this panel. You can click on this, and now I can see my current repository is GPU Workshop. And there's a button here that says pull latest changes. So, and there we go. I'm behind by 2 commits. So if I click this, then it will successfully pull. So this is just a GUI version of doing like a git pull on the command line. And you could certainly, you could go in here and launch a terminal and do it similarly in the terminal if you're more familiar and more comfortable doing it that way. But anyway, if I go back to the file browser, now that I've pulled the changes, I can go to the O4 soft infrastructure directory, and you should see that there's this building GPU code IPython notebook. So I will click on this and it will load it up. Now, I called it an IPython notebook. Actually, we're running a different execution kernel. So I'm guessing most people here are familiar with Jupyter Notebooks at this point, but in brief, this is just a file that is a combination of decorative markdown text that gives context, and then interactive cells of code that I can run as part of that notebook. And those cells will run based on whatever kernel I have selected. So in here, I actually have a bash kernel running instead of a Python kernel. And that sort of means I'm running a shell in the background. So I can just run shell commands and do like module loads and run compilation commands. The only other thing I would note about these notebooks, if you haven't used them before, when you click on a cell, if you just want to run that particular cell, you can type on your keyboard, you can hold Shift and type Enter, and then that will run that cell. So that's how you can sort of follow along in this notebook. So we're going to build some GPU code, and then we're going to monitor the execution. The first thing that you'll want to do is configure your environment. So the default compute environment on Casper, it provides the Intel compilers for CPU workflows. And obviously we want to do GPU work, so we're going to switch to the NVIDIA HPC SDK. So again, if I run that module avail like I showed earlier, that will show me all the versions of NVHPC that are available on Casper. There's the default. We're going to use the latest. We're going to use the 22.2. So I'm going to first clear out all of the other modules that may be loaded with a module purge, and then I'm just going to load the 22.2 release of NVHPC, and I'll list the modules that I've loaded at that point to make sure that it's what I want. So there we go. NVHPC 22.2 is all I have loaded. So now I'm ready to go. What we're going to do as part of this first demonstration is compile a basic OpenACC Fortran code. We're going to take this example from the HPC SDK examples. So the first thing that we need to do is we need to make a copy of the source file at a location in which we have write permissions. We can't build and run the executable in the HPC SDK install because that's done with privileges that we don't have. So we're just going to make a directory and copy a single source file from a very simple example into that directory. So I will run this cell, and there we go. I ran an ls, and now I see that I've got this single Fortran 90 source file in the directory. This code contains a few OpenACC directives. It just offloads some scalar multiplication operations to a GPU. You can certainly look at it in a text editor if you're interested. But we're going to sort of treat it as a black box in this session. The details of the OpenACC programming itself is going to be taught in future sessions. In fact, the next session will start that process. So for now, we're just going to only focus on how to compile this code so that you're prepared to do so quickly and readily in future sessions. Since this is a Fortran code, we're going to obviously use the NV Fortran compiler. And there's a key flag here to actually enable OpenACC directives to be processed by the compiler. And it's this -ACC flag. So that has to be given to NV Fortran in order to enable those directives. Otherwise, it'll just compile the code for serial CPU instructions and won't do any GPU offloading. So if I look at my compilation command, I can see I have the compiler here. So it's NV Fortran. I'm asking it to output an executable, which I'm calling ACC_F1. I'm enabling the OpenACC directives, and I'm providing the source file. And I can run this cell here, and I've got another ls. So now I can see I've got my source file, I have my executable ACC_F1. And if we were doing, more computing, I suppose, then we could run this binary, but we're just happy that we produced it here. Now, we could just trust that the compiler has used OpenACC, and in general, you will. But there are a number of ways you can verify that OpenACC was actually used. One is to use the strings utility, that's sort of a basic Linux utility. And this can extract human readable text from any file really, but it's typically used on binary files. So we extract some text strings, and then we can search the output using grep for any references to libacc, which is like the OpenACC libraries that are going to get built into and linked into this executable. And if we use the -M1 flag, we can restrict grep to only give us one response, so we don't get a huge long list of strings. So if I run this code now, I can see that I've echoed OpenACC libraries, and in fact, libacchost.so was a reference to that was found in our executable. So that tells us that OpenACC was used by the compiler. To do a counterexample, if I do NV Fortran again, and I output and I create a binary this time called noACC_F1, same source code. But I'm not giving it the -ACC flag to enable OpenACC directives. And then I run the strings command on this grep for the library. And here I've put an OR condition. So basically, if grep returns nothing, just echo none found. So it's a little bit more exciting than a blank cell. But if I run this now, it says OpenACC libraries none found. So there we go. If you don't have that on, OpenACC won't be used. Now, similarly for OpenMP GPU offload, it's a lot of the concepts translate very closely in terms of compilation and optimization, but the actual flag to enable the offload is different. So instead of a -ACC, you would do a -MP = GPU, and that's how you enable GPU offloading with OpenMP 5 code, or 4.5 code for limited feature set. And here, this is, I don't have this code, this isn't a cell we can run, but if you have an OpenMP GPU offload example, that's how you would do it. And if you just do -MP, it's going to do CPU offloading, so the =GPU is important there. Now, that's a very basic example. We can, of course, get additional acceleration information from the compiler itself, so we don't have to rely on strings or LDD or anything like that. The NVIDIA compiler provides some diagnostic options. There's a flag -minfo in particular, which is quite powerful. And this allows us to learn about compile time decisions, including GPU offloading. So it accepts a bunch of options. And one of the options, or one of the arguments, is accel, which you can imagine is short for accelerator. And that will give us information specifically pertaining to OpenACC or OpenMP GPU acceleration at compile time. So here I've got the same compilation command with this NV Fortran, I've got the -ACC, but now I'm adding minfo = accel. And if I run this, now I can see I've got some information about what it's doing when it runs through the OpenACC directives and/or pragmas. So the details of this we'll cover in future sessions, but generally, if you can read through this, you can see there's some data copy operations, there's some loop parallelization, maybe a bit of vectorization. But the important thing for our purposes is generating NVIDIA GPU code. So that's another confirmation that it is using OpenACC as we want. Alternatively, you can specify -minfo by itself without the Excel argument. And that's going to give you a whole lot of information about compile time decisions, including the acceleration information, also loop optimizations, loop parallelizations, loop vectorizations, some more as well. But one thing to note about this is if you use -minfo by itself, you'll get both CPU and GPU diagnostic information. So it's a whole wealth of information, but it may be more than you're looking for at that particular time. We can also customize how OpenACC will offload, and in particular, what architecture it will optimize for as it does that. So new GPU generations almost always provide new features and capabilities. It's part of, their process of getting you to buy new hardware. The NVIDIA compiler allows you to generate code for one or more specific GPU compute capabilities. This would be like generating code for different architecture optimizations on the CPU as well. For example, the GPUs at NCAR fall into 3 categories. So we've got those GP100s. They have a compute capability of 6.0. The V100s have 7.0, and the A100s on Derecho will have 8.0. If you include more of these compute capabilities when compiling, the compile time and the size of the binary file will grow, but you'll have an executable that better matches the optimizations of each target GPU. And as implied there, you can use multiple compute capabilities in a single binary that gives more code execution paths, which is why the size of the binary grows. Now, if you click on this link, you can see all of the GPU compute capabilities for the different architectures. It's certainly quite a superset relative to the 3 types of GPUs we have here at NCAR. So I'm just going to show some examples with that same OpenACC code here. In the first example, I'm compiling for the GP100 and the V100, and I'm going to time my compilation command here just to see how long it takes. Note now that I have this extra flag, this -GPU, and I'm giving it the CC60, CC70 options there to indicate that I want both of those compute capabilities. I'll run this, and we should see it compiles quite quickly. Now there is another option here, this CC all, and that's going to compile your executable for every compute capability that's supported by that release of the HPC SDK. So if you want something that sort of has a max portability across different GPU architectures, that would be an option you could use there. But if I run this, we'll see that it should take a little bit longer, and eventually we'll see that it produces a bigger binary. So you see it took about 4 times as long to compile for this code that's negligible, but it might not be for a complex code. And if we compare the sizes of each of these, I'm just running an ls-l and -h for human readable, and I'm looking at my 2 binaries. I can see that the one with all the compute capabilities is more than twice as large as the one with the 2 compute capabilities. So yeah, there are trade-offs there, but that gives you flexibility in terms of how you're building your executable. The default compute capability, this is a bit tricky and a bit confusing. So what it chooses by default, if you don't specify, depends on where you're compiling. So if you're compiling on a host that has a GPU, in particular a GPU that is supported, so like if you have a at-home GPU for gaming, it's generally not going to detect that. But for general purpose GPUs, for example, on Casper's GPU nodes, the compute capability of that GPU that it sees is what will be used. If, however, you're on a node that doesn't have a GPU that it recognizes, for example, Casper's login nodes, the binary will be compiled with -GPU equals CC all. So you'll get that fat binary that has all the different compute paths in it. So you will get a different result depending on where you compile if you don't specify that explicitly. And an interesting thing too, if you do -GPU equals and you specify a specific compute capability and you're on a node that doesn't have any GPUs, it'll give you an error. So the behavior here is quite inconsistent. And it's best just to sort of be explicit and think about where you're compiling. Since we're running this on a node with GP100s, when I compiled this one up here, it actually used compute capability 6.0 since that was the GPU that was found. So, I've mentioned a couple of options, the -ACC, the -GPU. There's a whole ton of options, as you would imagine with any compiler. And as with many Linux programs, one of the best ways to learn about all the features and configuration options of each compiler is to examine its manual page. And you can do that at the command line by running, for example, man nv-fortran, as long as you have the NVHPC module loaded. And I've taken a small snippet of that manual here. So this is by no means, exhaustive. But this shows a little bit of the entry describing the -ACC flag. And we can see from this that in addition to just being an on-off argument, it also has sort of subcommands that you can issue to the -ACC. So the default behavior is to compile OpenACC directives for parallel execution on the GPU. That makes sense. But we could actually specify here to do serial execution of those OpenACC directives on the host GPU, or sorry, host CPU. That's obviously going to sort of be like an emulation mode, but that could be something if you just want to debug and you don't have access to a GPU. And there's a whole bunch of various options to the various flags. Like there's a similar section for the -GPU. So I highly recommend that you take a look at these manual pages as you have time and as you need. So now we're going to switch gears a little bit. We're going to talk about compiling a CUDA Fortran program. So this CUDA Fortran program consists of multiple source files, so it's a bit more complicated. And as a result, we're going to switch to using a makefile for the compilation. Just to note, this program uses accelerated CUDA fast Fourier transform routines. So it's sort of like FFTW, but for the GPU. And as a result, we have to link those libraries into our executable via arguments to the compiler. So again, the first thing that we're going to do is we're going to copy the source files from the HPC SDK directory into one that we create in our personal space here. So if I run this, I can see that I've got 3 source files. I have these 2 modules, and then I have the main code itself here, the CUFFT test.cuf. So all of these are CUDA Fortran file extensions. Now, again, we have 3 files we need to compile and then link together. We could do this interactively on the command line, as we did before. We could write a shell script to contain these commands, but the standard way to build many open source applications in a Linux environment is to use a makefile. Odds are you've probably run a makefile before, but I'm guessing less of you have written a makefile. So a makefile simply defines a set of targets, and you can think of these targets as implying rules, which are then interpreted by the make program itself to execute commands. Basically, it's a way to generalize our compilation and linking steps into a defined set of rules. Now, before creating our compilation rules in our makefile here, it's helpful to define some settings. And we're going to define these in the form of variables. So just like if you were writing a shell script, you'll probably have a section at the top that has a bunch of variable definitions. One thing to keep in mind is that while these may look like shell variables, they follow a different syntax. And if you just sort of use your shell knowledge to define things here, you're probably going to run into some errors. So here I'm using just the command line utility cat to output this block of text and write it to a file called makefile. So what am I doing in here? First, I'm defining a variable fc, and I'm saying if that variable is not already defined in my shell environment, define it to be NV-Fortran. That's what this question equals assignment operator does. It says assign this variable only if it's currently undefined. Then I'm going to do a more standard variable definition here. I have this fc flags variable, and in here I'm going to provide some flags to the fc, the Fortran compiler. And the details of these flags, you can go on the man page and get more information, but basically I'm using -fast to let the compiler choose ideal optimizations for the target platform, and that's CPU optimizations. So that's like xhost for the Intel compiler, if you're familiar. And then there's this -m preprocess flag, which tells the compiler to preprocess all files that I specify when I use this flag. And that's important because typically NV-Fortran will preprocess files that it recognizes as Fortran files, things with like a .f90 extension, but .cuf is not included in the list of files that it detects. So by specifying this, we tell it to run the Fortran preprocessor regardless. And then finally, I define a variable here to contain my setting to tell the compiler how to use the CUDA FFT library. So there's this flag. Again, you can look at the man NV Fortran page, but it's -CUDA lib. And in there, I can specify a list of the CUDA libraries that I want to link into my executable. So here, I just want the CUDA FFT, CUFFT. So I define that to a variable CU libs. So now that I have that variable definition done, I can move on to the next part of my makefile, which defines my target rules. So again, I'm using cat. In this case, I'm appending instead of writing to the makefile. And I'm actually going to start off here doing 2 more variable definitions. I have this variable sources, and this is just a list of my 3 source files. So I've got the 3 files that I showed in ls above. So this is like just a text list here. And then I'm going to do a bit of a crafty variable assignment down here. So I have this objects variable, and I'm going to assign it to the result, which is this : assign it to the result of this string replacement. So this sources variable up here, I'm going to replace the .cuf extension to a .o. So that'll then be a list of 3 object files, and that's what I'm going to produce. I'm going to produce those 3 object files in my compilation steps. So for example, CUFFT test.o is in that list. And now I can get to my compilation rules. So in a makefile, this looks like target and then colon and then prerequisites. So basically, I have a target of my rule. This is what I want, and then this is what's required to make that happen. So I need these to be there before I can run the command that I specify. Now in a makefile, the first rule that you specify, the first target that you specify, is the default. So if you just run make at the command line, it's going to run the first one. So typically we would have what we want to produce, our final result, as the first target. So here I just have a target that I've named build, and the prerequisite for this is that I've already produced all of my object files. So this command won't run until I've produced my object files. So I'm actually going to skip down here to my second rule, and this is sort of a fancier one. This says my target is any particular object file. So this is a generalization. This % says it's a placeholder for any object file. So it could be this one, for example. And a prerequisite for that is the equivalent source file. So that has to exist. And since we've copied those into this directory, we know they do exist. Once those exist, then this command will run. And basically, this runs the Fortran compiler. It uses our flags. It says, compile this into an object. And here we've got another sort of special variable reference. This references the specific prerequisite target, or sorry, prerequisite, not target, for the invocation of that rule. So for example, precision_m.cuf would get put into here to produce the .o version of that. And once all 3 are produced, then we'll go back up to this build rule because our prerequisites have been satisfied. And this will run. It'll use the Fortran compiler again. It will output an executable. It'll use our 3 objects, and then it will use our CUFFT library reference. So that's our rules. We also have a clean rule in here just because it's always nice to give people a way to clean up their directory if they want to start over. But if I run these 2, we shouldn't get any output on the command line because I am redirecting the prints to this makefile. Now, one little sort of note here, JupyterLab replaces any tabs that you type with spaces, but make is picky. Make wants this white space to be tabs. It's sort of the opposite of, well, Python will accept either, but you have to be consistent. In any case, it's picky. So we're going to run sed here to replace any spaces at the beginning of lines with the tab character, again, to sort of restore the way the makefile needs to be. But if you were running this on the command line in a text editor, for example, you wouldn't have to run this sed command. This is just a byproduct of us doing this in a Jupyter Notebook. So now that we've prepared our makefile, it's all ready to go, we can run this, and hopefully that will make what our rules are doing more clear. So I run this, and it will output all of the commands that we've run. So it creates our 3 objects here from the source files, and it uses our flags. And then in the end, it takes our 3 objects, it takes our CUFFT library that the HPC SDK provides, and it produces our CUFFT test executable. And if I run ls-l, I can see all of these objects now exist in this directory. So this is a very simple makefile. It doesn't It's not saving you a whole lot over just running them interactively, though it is nice in terms of repetition if you need to do this multiple times. But you can kind of see, I think, from these rules, if you have hundreds of source files and you have a lot of operations on objects and things to link in, that makefiles are super powerful. And sometimes they get so complicated that then you use things like a configure script to generate the makefile and all of that. So, or in CMake, you use the CMake command. So this gets quite intense. But that should give you just a brief introduction to it. So finally, I just want to talk a little bit about monitoring GPU applications. So typical Linux utilities like top or PS, they're going to give you a CPU-centric view of what's running on the node. But NVIDIA provides additional utilities to monitor the GPU usage. One of the basic ones, but it's really powerful, is this NVIDIA SMI tool. So it has multiple modes of operation. I'm not showing all of them, but if you go on the man page, you can see them in depth. And these following cells, these code cells that I have here, demonstrate just 3 of the modes. So we have the default output mode, the device monitoring mode, and the process monitoring mode. So if I just run it by default, I can see information about the GPU. So it's Quadro GP100. I can see interesting things like the temperature and the power usage, memory usage, and compute. Basically, it's compute level. And I can also see a list of the processes that are running. And it's nothing too exciting right now. I've just got these X11 server actually for rendering, since this is more of a rendering node. But it'll show you the process IDs of those as well, and that it's running the graphics mode, not the compute mode. So this would be G or C here. I can also run the device monitor, so NVIDIA SMI daemon, and then this -C1 just asks for a single sample. If I don't specify this, it will keep running and keep monitoring over time. This -OT adds a time label, and -I0 says use GPU 0. So there's only one GPU on this node, so it's sort of not necessary, but if you're running on a node that has, say, 4 GPUs, you might want to isolate to just one of them. And here we can see some more information about GPU statistics, again, like temperature, shader, the shader core usage, things like that. And finally, we have the process monitor. This is similar flags, but again, we're showing this list of processes. And if I left the -C1 off, it would give me a running summary of those processes. And I think this is kind of nice, is finally, we can correlate the information that NVIDIA SMI gives to CPU tasks via those process IDs that it's providing. So for example, here I'm using a bit of just shell commands to take the first GPU command and get the process ID. That's what this awk does, and it stores it in a bash variable. And then I'm using that bash variable here to output some task information from the PS utility that comes from Linux. And if I run this, now I can see that that same process ID corresponds to this command that was run. It was run by root, because this is something that happens when the node starts up. And I can actually see how much host memory and CPU utilization this process has. And since it's not doing anything right now, it's very minimal. But this can give you some idea at a very basic level of how much GPU utilization there is and how much CPU utilization there is at the same time, using just those 2 utilities. Now, this obviously requires you to be on the node. You can script this up in a batch script, but oftentimes it's nice to do this interactively. And you can do this on Casper. So if you have a batch job that's running, the first thing that you would do is you would identify the node on which the job is running. And then you can SSH to that compute node from the Casper login nodes. So this would be an example of that. If I run qstat with the -n, so that shows me the node list, and then give the job ID, I can see which nodes it's running on. And if it's just one, it's simple. And then from the login node, I can SSH to that compute node. And then on that compute node in a terminal, I can run NVIDIA SMI and get all that same information and run those process monitors and things like that to kind of track the execution of my program. Now, it's important to note that you can only SSH to a compute node if you have a job that's currently running on that node. You can't do that at any time, but that's a nice capability to do some sort of interactive analysis there. So that's the summary of what we wanted to talk about today. You should now be able to compile basic OpenACC, OpenMPGPU, and CUDA Fortran codes on the command line, and maybe write a basic makefile. Certainly, we didn't go very deeply into makefiles, so if you're interested in that, I would highly recommend looking at a makefile tutorial. There's a lot of good ones online. And you can now get some basic diagnostic information for the GPU-enabled programs that you run. In the next couple of workshop sessions, we're actually going to begin the coding portion of this series, which is probably what everybody is really excited about. And then the next 2 sessions, we'll have an overview of using OpenACC directives and doing that sort of coding practice. So we look forward to seeing you there. And at this point, I can take any additional questions that people have. If you just want to put them in the chat, I see there's a couple of messages here that I think have been answered already, so that's great. But if there are any additional questions, feel free to raise your hand or type them into the chat. Can I point to a good make tutorial? Let's see. I found one that I thought was, if I go into makefile examples here, this makefile tutorial by example, it's a pretty simple start, but I think this one is a good starting point because it really goes into the syntax and it uses some basic examples that really only like echo before getting into using actual files, so you don't need to worry too much about having like source around and things like that. And it's organized in a very clean and easy to read way. So I think that would be a good one. It's probably why it comes up first in Google. Are there any other questions? I should say as well, if you've followed along just watching here, I would recommend that you run through this notebook later, if for no other reason that you make sure that you can run through this process when we get to more intensive interactive notebooks later when we do coding. Jesse, yeah, go ahead.
Hi, Brian. I was just curious for when you're compiling with certain GPU optimizations like the CC6 or CC7, whatever, if I compiled it with one version, but then I mistakenly run that executable on a different GPU, will it just fail or will it like just run with degraded performance?
So that is a good question. And I think we can run that as a test even in this notebook. So if I go back up here, let's compute this for CC7 capability. Right, let's go wild and let's make it CC8. Oh, that's because I'm in the wrong directory. All right, it's kind of funny when you're in a notebook instead of a terminal. There we go. So now we've compiled this, and I'm just going to add a cell here, and we'll try running it. Oh, it worked. So that was kind of my suspicion, is I feel like if you're, and I don't have a ton of experience with that, so if there's somebody in here who has run into problems, I would encourage you to contribute. But I would suspect if you're not using the enhanced capabilities that it's going to run. But if you're using something that will only work, for example, on the Ampere, that I could see running into some problems. Davide, do you have a comment on that?
Yeah, I mean, I don't know for sure because I haven't experienced this issue myself with the GPUs, but I've seen it extensively with the CPUs where, the different x86, new ones introduce new opcodes that the compilers know. And if you compile, for the latest Intel CPU and then try to run it on an older one, it might work. Because it depends on what the compiler decided to use of that newer CPU, and so if whatever used was already existing on the old one, then it just works. But you never know for sure, and so it might, in the case of on the CPU, it will fail with an illegal instruction error. If it does, because that will be exactly what happens, that the compiler inserted an instruction that's illegal for that particular architecture, and so the older CPU would fail that way. I would expect something very similar here, that if you do this for simple code, maybe the compiler doesn't think there is anything fancy that it needs to insert it, but if it does, then it will fail in a possibly weird way.
Great. Yeah, that all makes sense. Yeah, thanks.
Sure.
Yeah, I was really hoping that it would just print this horrific error because it would have been a more impactful demonstration. But I guess it's nice that you get a little bit of play there, depending on what the compiler decides, like Davide said. All right, are there any other questions? Certainly happy to stick around for another couple minutes. If not, please do post them in the Slack channel as they come up. We definitely want to sort of make sure everybody's on good footing in terms of this base material before we get into the coding in 2 weeks. And I guess I should say as well, if you did have any trouble accessing like the Slack workspace or the GitHub repository, just send us a ticket and we'll make sure that those permissions are set up properly. All right, well, I think I don't see any questions coming in, and I see some thank yous. So thank you for your time, for attending. I think we'll wrap up the room here, but we'll look forward to seeing you in 2 weeks for the start of our Open ACC material. So take care.